Okay, sorry about that. That was just a mistake. I turned the computer off. It had clicked off on me and it got turned off. So let me continue. Let's look at a Guy-Lussac's law problem. Not Guy-Lussac's, a Dalton's law problem. Um, they might tell you something like this. The gas is collected over water. You collect 50 milliliters at a room temperature of 22 degrees Celsius. You collect 50 milliliters at room temperature of 22 degrees Celsius. Atmospheric pressure is 100.4 kilopascals, and the water temperature is 20 degrees Celsius. Okay, and then on the test, and you will have a problem like this on the final, so it's similar to this. On the test, it'll say the water vapor pressure is, and I'm trying to remember, I think it's about 2.3 kilopascals for this. Okay, so what do we do with that? Well, what's happened is we have our volume. Oh, and then what the question would be is, what is the volume at STP? What is the volume at STP? So what we have to do is figure out what our volume, temperature, and pressure is, and then collect it over to STP. Well, the volume we've got, V1 is 50 milliliters. The temperature we have, and that is, and this messes students up, but it's the air temperature that we're interested in. Room temperature of 22 degrees Celsius or 295 Kelvin. It's the P1 that we have a little trouble with. Yes, atmospheric pressure is 101.4, but the pressure we're interested in is the pressure of the gas that we've collected. And some of that gas is water vapor. So we have to do this. The pressure of the atmosphere is the pressure of the gas plus the pressure of the water vapor. And this would be 100.4 is equal to the pressure of our gas plus the pressure of the water vapor, which we were told is 2.3 kilopascals. And the pressure of the gas, then, if we subtract this, is 98.1 kilopascal. And now we can set this up just like this problem. 50 milliliters times 98.1 kilopascals over 295 Kelvin is equal to volume times 101.3 and 273 Kelvin, and work the same problem. All right, now let me talk quickly about gas stoichiometry. Gas stoichiometry, there's two levels of it. The first one is a non-STP and the other is STP. And I'm going to do both of them together here. That's actually the way it'll be on the final. So let's just do a real simple problem. Let's say we take H3PO4 plus magnesium, and that gives me magnesium phosphate plus hydrogen. And you know what? I'm going to do something a little different here. Let's make this H2SO4. And we're going to make this lithium. This would be then lithium sulfate plus hydrogen. I need a 2 here, and that should be it. Okay, so let's say you were told you have 15 grams of lithium. How many liters of hydrogen at STP? Well, this is a real simple stoichiometry problem. 15 grams of lithium. 1 mole of lithium is, we're talking about grams. You never use 22.4 here. 1 mole is 7 grams of lithium. There's 2 moles of lithium for every 1 mole of hydrogen. Remember, hydrogen's a Brinkelhoff. And then this is where the trouble will be. 1 mole of hydrogen is 22.4 liters of hydrogen. How do I know that? Because 1 mole was always 22.4 liters at STP. And so we would multiply that out and we would have our answer. So it's 15 divided by 14 because of the 2 down here, and times 22.4. 15 divided by 14 times 22.4. I get 24 liters, which is kind of interesting. 24 liters. It comes out exactly 24. But now, let's say we change this problem. We're not at STP. Let's say this is at 100 degrees Celsius and 50 kilopascals. Well, what we do on that problem is we simply change this. 1 mole is equal to 22.4 liters at STP, but we're not at STP. So what I want to do is take PivNert, and I want to know what the volume is if I know everything else, and I happen to know everything else. I want to know what 1 mole is. This is 8.31. I'm running out of room, or I would normally write the rest of the units there. 100 is 373 Kelvin. And on the bottom, we'd have 50 kilopascals. And that will tell us the volume of 1 mole of the gas at that temperature and pressure. This is the volume of 1 mole of any gas at 373 and 50 kilopascals. So 8.31 times 373 divided by 50. And this actually is 61.9. 61.9962 liters. And so basically we would do the exact same problem now. 15 grams of lithium. 1 mole of lithium is 7 grams. There's 1 mole of hydrogen for every 2 moles of lithium. And 1 mole of lithium in this case is 62 liters, not 22.4. So 62 times 15 divided by 14, and we end up with 66.4 liters of hydrogen gas. Quite different from this one, but that's because the pressure and the temperature were considerably different. So once again, on this test, you want to, it's an essay format. You're going to need to type out and show me everything that you're doing. It's better if you say, I'm using this law, even if you type it out and this is what I'm doing. You should show me the changing the temperature. There won't be that many problems. There'll be plenty of time to get that done.